everyone, this is Srikanth as Assistant Professor of EEE Department. In this session, I am going to cover Zener diode and characteristics and applications of Zener diode. The mainly Zener diode is also called as a breakdown diode. That is nothing but a Zener diode is going to work in the reverse bias condition, that is reverse breakdown voltage. After a specified reverse breakdown voltage, the diode will work in the reverse bias condition. That type of diode is called a Zener diode. Here, which is going to have the same PN junction diode, only they are specifically designed to have a low and specified reverse breakdown voltage. So whatever the PN junction diode we are having, the same PN junction diode properties we are going to have for the Zener diode. Only the change is we are going to design a diode specifically with a less reverse breakdown voltage, so that this will take, whatever the diode will take, the advantage of any reverse voltage applied to it beyond the breakdown voltage. The diode is going to conduct in the reverse bias condition also. So in the forward bias direction, the anode is made positive with respect to cathode. The Zener diode works like a normal diode, which is going to have after the cut-in voltage 0.7, the diode starts conducting, so the current will start increasing. So here, this is the way we are going to get up to the cut-in voltage, the current value is 0. After the cut-in voltage, this is the voltage and this is the current value increases rapidly. So in the forward bias condition, the Zener diode is also work as a normal diode itself. So the forward current flowing through the conducting diode is at its maximum determined only by the connected load. By connecting a load, we can calculate the forward current which is flowing through the conducting diode. Thus, in the forward direction, the Zener behaves like a regular diode within a specified current and or power limits. The forward characteristics of a Zener diode is generally of no interest, because already we have studied PN junction diode characteristics under the forward bias. So similar way we are going to have the characteristics for Zener diode. So the characteristics under forward bias condition for both Zener and PN junction diode is similar. A conventional diode that blocks any flow of current through itself when it is reverse biased. When we go with the conventional diode is going to block the reverse bias current. So reverse current, when cathode becomes negative to the anode, then the reverse voltage reaches the predetermined value. Until it reaches the predetermined value in the Zener diode, then the Zener diode begins to conduct in the reverse direction. Whereas when we go with conventional, unless it reaches the maximum value, the conduction will not take place and the diode also will get damaged. So in this, because of the special design, the Zener diode is going to conduct in the reverse direction with a less reverse breakdown voltage itself. Since a Zener diode is work in the reverse breakdown region of the characteristic curve, they have fixed breakdown voltage, that is VZ value, which is determined during manufacture. The manufacturer itself will specify the Zener breakdown voltage in the reverse bias condition. So the reverse voltage across the Zener diode increases from 0 to the its Zener breakdown voltage. Once it reaches 0 to Zener breakdown voltage, a small leakage current will flow through the diode, which remains fully constant, and as the reverse voltage increases, once the reverse voltage breakdown voltage occurs, immediately the current leakage whatever the reverse current will increases rapidly. Once the reverse voltage is applied, where Zener diode exceeds the rated voltage of the device, a process is called Zener breakdown occurs. At a particular point of the voltage, the Zener breakdown occurs where the current will start flowing through the diode, which will limit this increase in the voltage. So when the current starts flowing through the diode, will limit the increase in the voltage. So the current now flowing through the Zener diode increases dramatically to its maximum circuit value, which is usually limited by a series resistor. Once the Zener breakdown occurs, the voltage drop across diode remains fairly constant. Once the Zener breakdown occurs, the diode is going to have a reverse current is constant, that is taken as IZ, which is taken which is we are going to have a constant value. The voltage at which the voltage across the Zener diode becomes stable is called the Zener voltage. Once the current starts increases, the voltage, Zener voltage, whatever the increase in the voltage is going to stop. So that voltage is called Zener voltage. For Zener diodes, this breakdown voltage value can range from a few volts up to a few hundred volts. The Zener voltage range will be from a few volts to few hundred volts will be there. And the point at which the Zener voltage triggers current to flow through the diode can be very accurately controlled. Here, once the voltage is triggered, there won't be any change in the voltage value because already the current is starts flowing. So voltage, there is no need to increase the voltage. In the doping stage of the diodes, the semiconductor construction giving the diode a specific Zener breakdown voltage, that is VZ. For example, it is 4.3 volts or 7.5 volts. This Zener breakdown voltage on the current versus voltage curve is almost a vertical straight line. When we go with the Zener breakdown voltage, once the breakdown occurs, current will start immediately. So the breakdown voltage will be constant for the Zener diode. Here you can see clearly in the forward bias condition, it is after the cut-in voltage, either 0.3, 0.5, 0.7, after the cut-in voltage, the current conduction will takes place. And for Zener diode, the symbol which is showing, the cathode symbol is showing like a Z. These two changes will be there corresponding to the Zener diode. Zener diode cathode is just represented like a Z. that is called a Zener diode. Here in the Zener diode, in the reverse bias condition, when we are going on increasing the voltage at Vz, at minus Vz, the breakdown is occurs. Once immediately breakdown occurs, the current is reaching the maximum value. Current is reaching the maximum value with the same constant Zener voltage. This is what we have, which is given in the previous slide. That is Zener breakdown region. Up to this point, the breakdown will never occur. Once this point is crossed, once the breakdown occurs, the current is going to rapidly increase the current. Once the current is increases, automatically the voltage will be stopped. Whatever the voltage which we have applied, that is going to be stopped at a constant value, and that voltage is called the breakdown voltage. Here the Zener diode is used in its reverse bias or reverse breakdown mode. That is, the diode's anode connects to the negative supply. From the IV characteristic curve above, we can see that the Zener diode has a region in its reverse bias characteristics of almost a constant negative voltage regardless of the value of the current flowing through the diode. So the negative voltage is almost constant regardless of whatever the current which is flowing in the diode. And here this voltage remains almost constant even with large changes in current, providing a Zener diode's current remains between the breakdown current Iz minimum and the maximum current rating. Whatever the current, diode current in the reverse bias is also should be within the limits, that is the minimum value, that is where the conduction is taking place, at which point the conduction is taking place, and the maximum current rating Iz maximum, at which the maximum current which can flow, which is flowing through the Zener diode. This ability of the Zener diode to control itself can be used to a great effect to regulate or stabilize a voltage source against the supply or load variations. Here, whenever, even though once the breakdown occurs, the voltage is making constant. That is, whatever the voltage across the diode is making constant. This ability is of the Zener diode to control itself can be used to regulate or stabilize a voltage source against supply or load variations. The fact that the voltage across the diode in the breakdown region is almost constant. Here, voltage across the diode in the breakdown region is almost constant, turns out to be important characteristic of the Zener diode. When this voltage is almost constant, which can be an important characteristic of Zener diode, as it can be used in the simplest types of voltage regulator applications. It can be used in the simplest type of voltage regulator application. What is the voltage regulator? Which is going to regulate the voltage, which is going to monitor the voltage. That is nothing but whatever may be the input you give, the output of the circuit is constant. Then that type of circuit is called a voltage regulator circuit. Here the function of a voltage regulator is to provide a constant output voltage to a load connected in parallel with it in spite of the ripples in the supply voltage or variations in the load current. So a Zener diode will continue to regulate its voltage until the diode's holding current falls below the minimum value in the reverse breakdown region. Here a Zener diode will continue to regulate its voltage until the diode's holding current falls below the minimum value. Once it is below the minimum value, then that diode is not conducting in the reverse bias condition, in the reverse breakdown region. Here Zener diodes can be used to produce a stabilized voltage output with low ripple under varying load current conditions. Where Zener diodes can be used to produce a stabilized output voltage with low ripple under varying load current conditions. By passing a small current through the diode from a voltage source via a suitable current limiting resistance Rs, the Zener diode will conduct sufficient current to maintain a voltage drop of V output. Here we are going to use the Zener diode as a regulator in order to give a constant output voltage. So for that, here we are going to give the Vz, and this is the input voltage which we are giving. Okay, so once this input voltage is given, so even though is there any change in the input voltage, this diode is going to give only a constant output voltage, which is going to provide a constant output voltage as Vz. So across the load, which is going to have a constant voltage Vz, and these voltages can be used in our stabilizers, which we are going to use in our day-to-day life for TV, fridge, AC. And in these stabilizers, this voltage regulator is going to be used. When this voltage regulator is used, even though there is any increment in the voltage, that will be cut out, and whatever the output voltage which we need for our appliances, that voltage will be given as the output. That is nothing but the Zener voltage. Here we remember that the DC voltage from the half wave and full wave rectifiers. In the diodes full wave rectifier, there are several ripple contents are there in that, and the DC source that has the load value changes, so to does the average output voltage. By connecting a simple Zener stabilizer circuit as shown below across the output of the rectifier, a more suitable output can be produced. Here in place of rectifier filter, we can also use this regulator, which will regulate our output voltage as a constant value. Now a resistor Rs is connected in series with the Zener diode in order to limit current flow through the diode with the voltage source Vs being connected across the combination. In series with the Rs, whatever the Zener diode which is connected to the Vs, so if there is any sudden changes in the source voltage, that has to limit the initial currents in the diode. So for that, a Rs resistance is added, and the stabilized output voltage is taken from across the Zener diode. Where Zener diode is connected with its cathode terminal connected to the positive rail of the supply, so it is reverse biased and will be operating in the breakdown condition, where resistor Rs is selected so to limit the maximum current flowing through the circuit. With no load connected to the circuit, the load current will be zero and all the circuit current passes through the Zener diode, which in turn dissipates its maximum power. A small value of Rs will result a greater diode current when the load resistance is connected, and large as this will increase the power dissipation requirement of the diode. So when the power dissipation, when Rs is there, when extra resistance is added, there will be a power loss. So we have to limit that power loss. That power loss can be minimized by taking care of selection of the series resistance value, and so that Zener's maximum power rating is not exceeded under this no load and high impedance condition. Here, when the load is connected in parallel with the Zener diode, so the load voltage is always same as the Zener voltage, because once the Zener diode conducts, there is no change in the Zener voltage. There is no change in the Zener voltage. So VR should be equals to Vz, and there is minimum Zener current for which the stabilization of the voltage is effective, and the Zener current must stay above this value operating under load within its breakdown region at all times. So the upper limit of current is of course dependent upon the power rating of the device. Here the supply voltage Vs must be greater than Vz. The main problem, one small problem which we are going to get with the Zener diode stabilizer circuit is that the diode can sometimes generate electrical noise on the top of the DC supply. So as it tries to stabilize the voltage, so there will be, when it is trying to stabilize the voltage, when there is a sudden changes in the voltage, there will be some electrical noise at the top of the DC supply when it tries to stabilize the voltage. Normally, this is not a problem for most applications, but the addition of a large value of decoupling capacitor across the Zener's output may be required to give additional smoothing. Whenever we want the additional smoothing, whenever we require a constant DC, wherever we require a constant DC, in that particular case, Zener's output may be required, and in order to get the smoothing, to give additional smoothing. When we summarize a little, a Zener diode is always operated in its reverse bias condition. As such, a voltage regulator circuit can be designed using a Zener diode to maintain a constant DC output voltage across the load in spite of variations in the input voltage or changes in the load current. Here the Zener voltage regulator, which consists of a current limiting resistor Rs which is connected in series with the voltage Vs. Once the Zener diode is connected in parallel with the load resistance, then that is called reverse bias condition. The stabilized output voltage is always selected to be the same as the breakdown voltage of the diode. Same as the breakdown voltage of the diode. Now let us go with a small problem. A 5 volts stabilized power supply is required to be produced from a 12 volts DC power supply input source. So the maximum power rating of Zener diode is 2 watts. Using the Zener diode regulator circuit above, calculate the first point, the maximum current flowing through the Zener diode. So the maximum current is nothing but power divided by voltage. Here the maximum power which is given in terms of watts is 2 watts divided by voltage which is given is 5 volts. So which is equals to 2 watts by 5 volts, which is 400 milliamperes. And the next one is the minimum value of the series resistor is Rs, where Rs is equals to Vs minus Vz by Iz, which is equals to 12 minus 5 by 400 milliamperes, which is equals to 17.5 ohms. The next parameter which is asked to calculate is the load current. If the load resistor of 1 kilo ohm is connected across the Zener diode, where IL is equals to Vz by RL, which is equals to 5 volts by 1000 ohms, which is equals to 5 milliamperes. And the Zener diode at full load condition, Iz is equals to Is minus IL, which is equals to 400 milliamperes minus 5 milliamperes, that is 395 milliamperes. Now, when the Zener diodes are connected in series, as well as producing a single stabilized voltage output, Zener diodes can also be connected together in series along with the normal silicon signal diodes to produce a variety of different reference output voltage values as shown below. Here this is 5.1, 3.3, 10 volts and 10 volts. Here it is of whatever the voltage, 10 volts, 10.6, 13.9. That is, every diode is going to have some conduction voltages that will be added. Here the final voltage which is given as 19 volts. Here if you take, this is the 10 volts Zener diode, and here we are connecting 1N4148. That is nothing but whatever the diode's conduction voltage is 0.6 volts, and this 10.6 is added to 3.3, that is 13.9 volts. So 19 volts. In order to conduct all these diodes, the minimum voltage which is required is the 19 volts. The values of individual Zener diodes can be chosen to suit the application, while the silicon diode will always drop out 0.6 to 0.7 volts in the forward bias condition. The supply voltage V input must of course be higher than the largest value of output reference voltage, and our example is given in this case is 19 volts. The next one is the This is another application of Zener diode, Zener clipping circuits. Here the diode clipping and clamping circuits that are used to shape or modify an input AC waveform, which is going to produce a differently shaped output waveform depending on the circuit arrangement. So the diode clipper circuits are also called limiters because they limit or clip off the positive part of the input signal, input AC signal. As Zener clipper circuits limit or cut off part of the waveform across them. So when we are going with the clipper circuit, this clipper circuit is going to limit or cut off the some part of the AC waveform, and they are mainly used for circuit protection or in waveform shaping circuits. For example, if we want to clip an output voltage waveform at plus 7.5 volts, we would use 7.5 volts Zener. If the output voltage waveform tries to exceed the 7.5 volts limit, the diode will clip off the excess voltage. If we are giving more than the 7.5 voltage, so whatever the diode is going to clip off, because diode, whatever the Zener diode which we are taking, that is going to gives the output voltage as only the Zener breakdown voltage. So once if we have chosen a Zener diode with a breakdown voltage of 7.5 volts, then even though you change the input, the diode will give only the 7.5 volts itself. Here you can see clearly a sine waveform when we are giving a single Zener diode is connected. That is nothing but it will work this Zener diode and a resistor is connected. So once the Zener diode is connected, one single Zener diode is connected. So this is, let us consider this voltage as VZ. When this is the VZ, once it reaches the VZ, the diode will start conducting, and this will not allow the increment in the voltage. This VZ value will be constant. And in the same way, here VZ value is also constant. So at a particular value, you can see clearly this is the dotted line which is given, and whatever the waveform is going to be clipped at this particular line in the positive values. When we want to go with both positive and negative values, then we have to go with double Zener diode clipping. Here we are going to take two Zener diodes. When we take two Zener diodes, this clipping portion in the positive half cycle and this clipping portion is in the negative half cycle. This is clipping position is going to happen with the Zener diode. Now a back-to-back connected Zener diode can be used as AC regulators, which is producing what a jokingly called a poor man's square wave generator. This regulator is jokingly, we can call it as a poor man's square wave generator. That is approximately we'll get some constant. We're going to get the voltage waveform will be like this. So which is approximately nearly square wave. That's why it is called poor man's square wave. If we wanted to clip an output waveform between two different minimum and maximum values of say plus 8 volts and minus 6 volts, we would simply use two differently rated Zener diode. Whenever we are having two different values of plus 8 and minus 6 volts, and note that output will actually clip the AC voltage between 8.7 volts and minus 6.7 volts due to the addition of forward biasing diode voltage. So when we are having the ratings of the diode will be different, that is 8.7 and minus 8 and minus 6. So in the positive off cycle, it is going to clip at 8.7. In the negative off cycle, it will clip at minus 6.7 volts. In other words, peak to peak voltage of 15.4 volts instead of expected 14 volts. As the forward bias voltage drop across the diode adds another 0.7 volts in each direction. In both positive and negative off cycle, this cut-in voltage is going to be added for the diode. And here Zenars are generally placed across the power supply input terminals, and during normal operation one of the Zener diode is off and the diodes have little or no effect. So this Zener diode will be once if we have given the supply input terminals and during normal operation, one Zener diode will be under off condition and the diodes have little or no effect. However, if the input voltage waveform exceeds its limit, then the Zenars turn on and clip the input to protect the circuit. When the charge carriers move across the junction, the electrons combines with holes and energy is lost in the form of heat. But also some of this energy is dissipated as photons, but we cannot see them. If we place a translucent lens around the junction, a visible light will be produced and the diode becomes a light source. And this affects the producers of another type of diode commonly known as light emitting diode, which takes the advantage of this light producing the characteristics. Because when we are going with the LED, we are going to talk. What is LED? Light emitting diode. That is, when a light falls on the diode will start conducts in a variety of colors and wavelengths. The light can be of in different colors and different wavelengths. So in this session, we have discussed the Zener diode characteristics and Zener diode as voltage regulator, clipping circuits using the Zener diode. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.